Good? Okay. So last time we ended with basically how to use a graph to be able to chart out dependencies and things of that sort. What we'd like to do is be able to now start talking about how to use this on one of our techniques. Now, I'm a big supporter of what's called hardware-software code design, which basically means that you can't really design one without the other. Software people need to understand the hardware, so like if you're a compiler person, you really need to understand the hardware to do a good job on the compiler, particularly if you're the back end. Compilers are split into two halves. It's kind of the front end that takes the language and puts it into this kind of meta-descriptive language, and then there's the back end that takes that description and then puts it onto the particular hardware platform that it's going to. But even for the front end people who theoretically are all in just software land, converting from one language to another, you really kind of want to think about what will be able to be put onto machines. So you have to kind of think through, you know, the general process of what is architecture in general for most machines. Because there are types of things that are done, and there are types of things that would be not as easy to phrase. And so if you're able to organize things in a way that's going to more easily go down, it makes the back end a lot easier to design. But it's also true for hardware people. We sometimes think, well, we build it and they figure out how to use it. But well, that's true in some sense. It's also not true. We're building specifically for their use. And there are certain things that are going to actually perform much better if the two work together, because they have different pieces of information. At runtime, you have the value of the variables, which you do not have at the pre-time, because a lot of it is user dependent or detector dependent or tons of other things where your data is just not available to you in advance. So you cannot make that determination a priori. But there are also some things that can't be done at runtime. For instance, we can't see all of the code, nor do we have the time that it would take to sometimes do all the dependence analysis that would be needed to look at a larger block of code. Therefore, it's more efficient to do that in advance when the compiler can run as long as it really wants, going back and forth, looking at different things, and therefore potentially storing us prefetch commands and all kinds of other things. So there's a ton of techniques that are out there. What I'd like to be able to do from the software side is to consider probably the most basic one, which is loop unrolling. And that leads to the question of, how far can you unroll the loops, and that leads to the GCD test. That's kind of the one side of it. And then, if we get a chance, I'd like to be able to talk about software pipeline, which is kind of a different way to do slicing of the data to make these. And it's got some kind of cool advantages under certain situations. So, let's consider the idea of what's going on with, the idea of loop unrolling. Let's say I've got a loop, and it's just got a few commands that are within it. Okay? And say, for instance, I was just doing something where I wanted to, let's say, load a vector. And so I was going to load to, we're looking at two floats. We'll just stick with regular. Actually, maybe I'll use their T notation. So I'll do to T0, and I want, let's say, offset 0 from S0, and then add to T1 and T0, and then I want to add I to S0 and -1, and let's say set on less than, let's say S0 from S1. Oops. S0, S1. We'll store that in T2 and edge equal to 0 on T2 top. So consider this loop. Right? Anybody tell me what that loop does?
value from memory and then does something else.
Yes, so maybe it will help. I'll put another line up above here. It's kind of initialization.
You're summing a range of values,
I'm summing
or like 10 down to 1 or something like
an array. Yeah. So summing a vector array. So this one right here will sum up a vector. Yeah. So this is where it's loading from the vector, adding it into the running sum. This thing that I added before just initializes the running sum. Right here I'm decrementing as it's going on, and I'm checking if where my current pointer is where the start of it is against it. Putting the value, if it's less than that, it'll set it to true, otherwise it's false, I'm not done. So if it's equal to 0, it's not done, and so it'll go back to the top and keep summing. So, all right, so I got my nice little loop here, and away we go. Now, not all of these are, you know, kind of equally easy to do. There's obviously some ones that have some slowdowns in them, so on and so forth. Let's take a look at dependencies also. I'm gonna just label our lines A, B, C, D, E, the parts in the loop, because that's the part I care about. So I'm not worried about anything before or after. First thing we want to do is kind of get a graph going of what's going inside of these. So we'll start off with just A, right? So I've got A in here. B. Any dependence B has on anything? I can show B depends on A. How about C? So C, it can't go before it, right? This is, remember our war and our was, right? We just did those as dash lines. It's just saying, hey, there's a name dependence here. So I'm just kind of grouping those ones together on my graph purpose to let me know, you know, hey, we're both using S0. Now, which one am I? Am I war or am I wa?
Well, you were reading the first time.
Yeah. So this is war. This means war. Sorry. I never claimed to have good humor, and you knew that when you signed up. Okay, next one. D.
C.
How about E?
Depends on D.
All right. Now, I could nicely on a single machine, single pipeline machine, I can schedule A, B, C, D, E, and I'm fine. All right? I can even, since A might be a little slow, I could even potentially, you know, go A, C, D, B, E. The only thing I would note to you is E is a branch, so I just put my little notation here just to let you know, hey, that's, you can't go past that line without some safety. There are some ways you can actually schedule something after it. That's if there's a branch delay slot and you can schedule it. Okay. So if your particular architecture has a branch delay slot, and it's user accessible, then by all means, we feel welcome to get whatever number of spaces after. Everybody knows branch delay slot, BDS? What's, no? Okay. When you're doing code, remember that you've got, you know, blah, 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 and then there's a next command here, whatever, you know, F, G, H. When it's fetching things, since we're in a book that's on MIPS, let's consider that. So let's say it's, you know, at time 0, it's fetching E. right? Has no idea what E is. That means it's already done, you know, D, C, B, A. So then we move on to time 1. E has moved on, and all the rest move on. A finished, J, whatever, right? We go to each one in turn as it's going in, but I'd like to be able to know what to put in here. But that kind of depends on when E finds the answer. When does E know what's going on? So, when amongst this chain for a MIPS machine does E have the answer of what the new command is?
At the end of execute?
So, it does at the end of execute, it's done the calculation. But for a MIPS machine, it hasn't taken that result because it took the entire period to get the answer for doing the comparison. So it outputs a 0 to you. And then you've got to do 0 and branch in order to determine should I really jump. So your AOU in the execute phase has the output of the result. And it also has another line called 0, which was the result equal to 0. That's what's used for branch and turn. But AOUs take a while to calculate stuff. And then you also have this control line called branch. Was it a branch command? Since there's no time left to do anything, there's just enough time to get the answer into the buffers, they just pull the answer in. And then that's the one that does the selection for PC source. This is the one that selects what goes into the program counter. So there's that one little AND gate just into your next stage. You know, depending on how that is, there might be enough time, depending on the delay on when the PC source thing locates. But that means you're basically going to get your next one at this if you're lucky. Let's assume we're lucky for the moment. That means I would know, at this point, let's say the loop was going to continue, I'd have A. But then, what's this?
Yeah. What is that?
Yeah, we call that the bubble that's going on. It's a bubble in our pipeline. Kind of just like you might have a gas bubble in a pipeline that has liquid in it and that. And this is what's causing performance loss as it's going on. When you look at these for my whole system running, you know, I've got 5 commands in here, but it takes 7 to actually execute and run this. So efficiency-wise, I'm really only running at 5/7 of whatever's going on. So those 2 commands are really profoundly important in the overall run of it. Now, what people do is they go, these ones right here, I'd like to be able to take advantage and stick something in there that'd be a useful command. If the compiler could tell me in advance what to put in there, and for instance, reorder the pipeline that's going in. Like for instance, maybe it decides to pull B out and stick B here. Would that change anything? Would it hurt anything if I guaranteed B was going to be pulled along with it? Right? If this had a little branch delay slot, you know, a little seat for something, and I stuck B in that seat, so it's guaranteed to go along with the rest of the group, would it damage anything to cause it to go after these? Well, the only reason it would is if there was some type of a name dependence that was going to cause a problem for it. Is there? For B, no. So I could stick B there. And that means I've improved. The whole thing now took me 6 times to go through. All right? So, I mean, that's a definite improvement as we go into things. So we'd like to be able to do that. Now people could say, hey look, maybe I could even schedule 2. And there are some machines that do up to 2 stuff. The initial IBM RISC 6000s actually had 2 that were available to you to schedule. Now, this looks like the awesome answer to end all answers. This came up, it was very popular in the 80s, which is why MIPS does it. That's going on. Now the question is, as a human, I can actually do a pretty good job of scheduling. But that would mean you would need human beings doing all your assembly code. So human-done assembly code was popular for really efficient applications through the 80s into the early 90s. Actually, that's how I started my career. I got hired out of school and I was doing assembly coding for military aircraft. And got pretty good at being able to schedule these things that goes on. But the question is that really practical to have human beings scheduling a lot of assembly code? Not tremendously. It'd be a lot better to have a pretty good compiler that will do this free and very, very fast. And if a human has to intervene at a tough point, let the human intervene. Question is, how well can, and let's even just leave it at 1 slot, how well can a machine schedule 1 slot? Is there a way we can determine that? Yeah, so what would we do? If I gave you that thing and I said, hey, for our machine, I need to know how well we can schedule that branch delay slot to determine, do we want to do this? How would you do it? So you could write one to check the dependencies, and you could actually build the machine that would do that scheduling. Once I've got something that's going to do the scheduling, how do I know how well it's going to work? Yeah, run it on a whole bunch, try it. Run it on a huge number of cases that's out there. And then I can just take statistical information, find out probabilistically how often does this do this. So your guess, compilers, right, and MIPS is noted to have one of the best compilers in the world, right? They basically had Stanford and Berkeley grad students working on making really, really efficient compilers for this to schedule those slots. About where do you think they're at percentage-wise, if you had to take a guess?
2.
Okay, we got an argument for 10%.
50.
We got a 50. We're saying, how often can it schedule that slot?
Effective use of that slot.
99?
What?
99?
So we're gonna get a wide range of somebody
Someone's
that's
right.
gonna do well.
That's right.
It's a good strategy,
Yeah.
cover
Yeah.
the bases.
Yeah.
This is kind of like the Price is Right idea. If you figure that, I got everything above it, because.
Low, high, in the middle, yeah.
Any other guesses?
High.
I think it's gotta be high somewhere in this zone. So pick like 98, like cut him right off.
Right,
Yeah,
it's true Price is Right.
Yeah, I don't know, but I'm gonna make his likelihood impossible.
Yeah.
Do we feel it's probably close to one of these?
I'll bet it's between 0 and 100.
Yeah. Pretty good guess. If it's not, then you should suspect my answer. Believe it or not, it's in this range.
Yes.
All right, it's about 40–45%. Depends on the code.
Okay.
All right, and that's a really awesome one.
Yeah. But I went over, so 10%.
So technically 10% wins, yeah. Well, no, actually, no, 50% should win, yeah, because the 10% it's past there. So, so whoever got that wins the brand new car.
Aston Martin's that good.
Yeah. But my point on this is computers are not particularly great. How often with a branch predictor can I fill those bubbles? Well, think when you're doing a loop, if I've got, how do branch predictors work?
Well, one way would be to figure out how often you're taking that branch.
So a branch predictor builds a small little finite automaton. Let's consider a small one, just a 2-bit one. This is probably the most common size that there's in. Right? And we take 2 bits, means I've got 4 states. Right? And so I've got a definitely taken, probably not taken, definitely not taken. So these are my states. If I'm a definitely taken and you take it, I'll put T for you took it. All right? You're gonna stay there. I said you were gonna do and you didn't. If I said you were absolutely gonna take it and you didn't take it, I'm gonna still be fairly confident, because I had a reason for this, but not quite as confident as I was before. You know, and we said it's more likely to take than not take, so we're gonna skew ours, although there are options for what you can do. If I don't take it, I'm gonna walk down the whole train. If I do end up taking it, I'm gonna go back. All right? If I don't take, I'm gonna stay down here because it's looking pretty bad for me. All right? But if I do end up taking it, now this is where you kind of get your decisions on how strong you want to go, is on this last set. Some people mirror it. Some people go like this. Because if I was, imagine you were doing a whole bunch of if statements. And if statements, depending on how you word them, you may or may not end up taking or not taking. In general, it's a good idea to try to always phrase things to take them, because then that kind of skews it. But if you know your machine can't do that type of prediction, then you should do it the opposite way. So if you have a machine that cannot branch predict, the easiest thing to do is not take. So you should try to skew it that way. But in any case, let's assume we've got a machine that has good prediction, so I take advantage of that. So I'm going to do a very aggressive on the take side. Like I said, some mirror back, some people make this one go across and that one go up. This is kind of all people's arguments of how likely is one particular area or another. Now the reason why I tend to want to put an emphasis here on the take is, assume I'm in the zone with loops. Right? Now a loop that's going on, right, for I equals 0, I is less than n, I plus plus, do something. Right? So assuming I had a piece of code at high level that looked like this, and I got a bunch of little instructions that are going on inside here, right, I'm going to do all these little instructions. I'm going to increment I, and I'm going to test it and repeat if the test was met. Well, starting from 0 going plus plus, I less than n, let's assume for the moment n was 10. How many times am I going to take it versus not take it?
You're going to take it 10 times, and on the 11th time, you're going to not take it, right?
I think it's maybe 9.
9.
Right, because it does the plus before the test.
Oh, right.
So it'll start testing at 1. Right? So 1 through 9 will be less. So I'll end up with 9 takes and 1 not take. Right? Is that a big number for n?
Not really.
No. Right? I mean, it's, you know, hundreds, millions. I mean,
Thousands, yeah.
if you take a look at the stuff that we do for our, you know, proton imaging, number of protons you could be dealing with would be billions, potentially. You know, hundreds of millions, tens of millions at the very, very least for a small cell. So you're dealing with tens to millions to billions, potentially, inside your loop that's going on. Yeah.
So not taken as a party, actually.
Yeah, not taken is pretty much really uncommon. It depends on your thing. You could get some stuff. If I'm stuck in 3D space or something, you know, I could have it 2 to 1, but even so, it's still 2 to 1. I mean, even if I'm just dealing with 3 vectors, which it's kind of hard to imagine loops being much smaller than that, because if it's smaller than that, why'd you write a loop? Right? So, I mean, if you're writing a loop, the likelihood is you're going to run it a bunch of times, but you can still only exit once. So I submit to you that, you know, if you looked at something like this, typically you start here, that's your start state. How correct would it be if I went even to my simple case with 10 things in there? It would be right 9 times, right? Because it keeps saying taken, 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 taken. It would be right every single time, no bubbles, right? Always guessing the correct amount. Right, taken, 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 One time it says taken and it wasn't. It was wrong one time. So what's my correctness percent? 90. So when you compare what I can do inside the machine compared to what I can do a priori. Now the advantage I have here is I have access to the actual data. So this is just telling you the actual data is more useful than the code for what's going on. Right? The problem they run into is not that they can't see stuff that can move. Even as a human being, the question is that command guaranteed to happen no matter what? And the question is, can you always move them? Well, sometimes you end up with dependencies between here, and you just can't move that one in, so you're in deep trouble. Right? So, you know, depending on how things go, that's where you end up with them, and I can often do better. So if I were to put a branch delay slot in, I couldn't use this technique to fill it. If you put a no-op there, I have to think that no-op is important and leave it. So whatever you schedule there must be honored here. So if you can't schedule, you put a no-op and I'm in deep trouble. Because now there's nothing I can do for it. So that low percent would kill over here. So that's why they're not as popular anymore. They can still be useful on machines that can't do prediction, that can't handle this very quickly. Then this is still a very viable alternative as it goes on. So for like a lot of embedded systems that might not want to afford that type of hardware areas to do it, it's a good idea to do some of the software techniques. Okay, you feel comfortable with that? Before we go on to fade them in? So now we see where kind of the issues are and what's going on. We'd like to be able to fill this more efficiently. But let's say I even want to take this one step further, because I can obviously fill this a little more efficiently by moving some of my things around. All right? Depending on how they go. If I put in one of those type of predictors, it'll correctly predict and it'll close this gap up immediately. All right? Particularly if I put in speculation and all kinds of other stuff to let me prefetch commands, all kinds of neat stuff. So let's say I've solved the problem with one pipeline. Now I've got two pipelines, hyper-threaded so they can access the same registers. So I want to schedule pipeline 1 and pipeline 2. So I could follow this and say, well, hey, look, I can do A, B sequentially in this pipeline. And if I do C here, there's no conflict, because this one's reading and that one's writing. So I just can't have this one finish before that one starts, but they're starting at the same time, so that's impossible. So this is completely safe because it's war. So I can just go C, D, E. Fine? Now, before it was taking me 5 cycles, maybe 6 cycles to complete a loop. So with, once I had the really efficient one that was packed, it was 5 cycles to do it. Now how long does it take me? 3 cycles. So now is 3. So if you look in that consideration, my speed up, it's 67% basically. It's a pretty good speed up. I mean, it's not the 100% speed up I'd love from a dual pipeline system, but it's still pretty good. So I could ask, could I get this to 100% speed up? The other way of taking a look at this is I've got 5 things filled out of 6, so my efficiency is 5/6. It's like, whatever, 80 some odd percent, right? So whatever, 84 or 83. So, I can go, okay, I'm 80 something percent and I've got a 67% speed up. Can I get to 100% efficiency, right? And 100% speed up, i.e. a speed up of 2. Can I do it? Well, I got 5 commands, 2 pipelines. With what I've got available here, no. So this is where loop unrolling comes in. Right? In loop unrolling, what I do is I say, well, look, what if I took a second copy of the loop? Right? This loop's going to run a whole bunch of times. What if I unrolled my loop? I probably should have put that graph under there because I want to continue down. So I'm going to put my next set down here, zero at they're online. Set less than T2 S0 S1. Now, I technically have to change this line when I unroll it, because right now it's going to the top, and when I'm exiting, it's going to run the whole loop again. So I need to make this a branch to an exit. All right, so I don't want set less than, I want something like a greater equal as a test that's going on, right? You know, and I'm not going to worry about, less than is the common test that they make available that's going on. I can obviously flip things and other stuff that's going on. So I'm not going to worry too much. I'm just going to allow that I can do this. If there's another test, because I could always rewrite for whatever language you read the test will go. And then I'm going to make this, now that I've flipped what my test is, I can just change this to exit, and away I go. And now this will run the same exact number of times as the original one. But now I've got more commands. F, G, H, I, J. So I can schedule these. Now, for each one of these when they're going in, I can look and see what are the dependencies between them. So we've already said A and B have a strong dependence between them, and C, D, E have their dependence chain, and we had that war dependence. And then we're adding in, starting at F, and it should be exactly the same because I copied it. F, G, H, I, J. Right? So I've got the same basic setup that's going on in here. Now the question is, what can I move across this line safely? Right? That's not going to affect anybody negatively if I do it. Now, I'm walking sequentially through my code. So the likelihood once I've fetched one thing from memory that this one's going to go all the way to RAM is very, very low. Particularly at the end of the loop, I probably aligned my memory blocks so that they were aligned to a block inside memory, right? I mean, even the most rudimentary compilers do that trick. So at the time I'm exiting, since I'm counting down, you know, as long as I'm within my loop area, I'm not going to get a memory miss when it's going. I'm going to get them as I move between one block to the next. So I'm probably pretty safe. So this command wouldn't actually hurt me to move back here, and it doesn't conflict with anybody. It would be a cache hit in any case. So that would be one reasonable way that I could go, is to just move F across the borderline. Now, would that help me? Well, then I'd have the two short strings together. So I would have, you know, F, G. Now G is a little bit past that line. So it wouldn't help me to put H there, and so I'd probably have to put H here, which means I has to follow it and J has to follow it. Did it help me? No, not really. So, and I can't really move them because these ones have to finish. I've got a strong dependence line between them. So that doesn't help me. Where do I need to put which string? I'd ideally like to take this one and move it into there. Does that affect anybody? Well, I've just got this name dependence. That's the only potential problem here. What if I remove the name dependence? What if I changed it such that I would really like H to finish before F does? What if I move this one, so I had H, and I did that? Would your opinion of where I could move it matter now? That'd be really easy to move across the border, wouldn't it? Right? So, let me find line H. And I'd like to move that before F. So now assume I've moved it. Now what that means is, this one is going to see S0 that's one thing too small. Now in all likelihood in MIPS it'd actually be -4 or something, but I'm not going to worry about that, that's just a scaling issue. Right? But that means this one should get a +1. That's really easy to change. Or a +4 if you were dealing, who cares? If you're dealing with a machine that's, dealing with 64-bit +8. So I'm not worried about that, right? Just make sure you understand the idea. I can shift it, and this is where I can use displacement addressing mode to my advantage. I can move that and make it look as if it was required. I've now made this style. Now I can move that one in here. And so I can just go H. I can continue F and G in the same line, and I and J. Now what does my efficiency look like? I've got 10/10 filled. All right? How about my speed up? I'm taking 5 cycles to do 2 loops, and it used to take them 10 cycles to do those 2 loops, even with their best system. So my speed up is 2 at 100%. This is where loop unrolling comes in. There's always that little bit of a trick where you have to make the jump out. And then the question is, you're always trying to take this graph and move it, and you have to pay attention to where those lines are. Right? Does it make sense? Do we want another example? Do we want to move on to software pipelining? Does somebody want to come to the board and get the amazing calisthenics and, now 9 o'clock in the morning of walking up there? So where are we at? We want to do another? Do we feel good with, do we understand the idea? The first thing is concept, right? When you go through in any class, the first thing you want to do, you get a theory, and then you figure out, okay, how can I apply that theory that's going on? And that should lead to understanding the concept. If you get the concept, then what you need to do is practice to make sure you got the idea down and that you can use it. If you're at the point where you understand the concept, a whole bunch of examples won't help. I actually do have more examples in my online notes. So I would encourage you to go in, and when you do those examples, they're in kind of a text style where I present a problem and then I immediately solve it. But read it, don't look at my answer, try to solve it yourself. And then see if you can come up with, now, were there alternative ways I could have potentially rescheduled this thing? Yeah, I mean, there's a whole bunch. Could I have technically swapped A and C with leaving the others? Could I have swapped B and D? Right, so I could swap left to right and I could get an intermingling of those and it wouldn't matter, would it? It's often a little better. You'll notice I try to stick all my loads on one line. Some machines only allow loading on one side and branching on another. So they don't give you full pipelines. On some pipelines they give you the memory instructions, on some they give you the branching, so that you can't end up, I mean, what would you do if you had 2 simultaneous branches? Should you branch or not branch? Right? And I can obviously give you multiple pipelines, but if I give you multiple memory loads, I've got to increase the bandwidth to your memory, which could potentially be expensive. It might be the only thing that keeps your system alive if you're a very data-hungry application, so that might be necessary. But it's obviously more complicated that goes on. So some systems try to do that when they go on. Some are completely open as it goes, but most people at least restrict you on the branch area, because nobody wants to deal with multiple branches. You know, one says branch, the other says don't. Right? What do I do? What do you do if both say branch and have different addresses? Should I branch or should I not, right? Okay, so if you feel good with this and you think you can do it, try some out and then come talk to me if you have problems. Let's talk about software pipelining then. Software pipelining does a completely different idea that it goes through. It's actually kind of a cool idea. So I've done, for other stuff, these lovely little copy and show you fetching and whatever else as it goes. So consider for our case, we could have, let's just assume the original code that we had. So it was A through E and it branched to top on the normal that's going. So on a normal one, it were on A, B, C, D, E. Now, I could have a second system that starts it, another one just a little bit later, A, B, C, D, E. A second one off one in time. So this is kind of first iteration, second iteration. And I can do that for several different ones that's going on. And we do this for however many copies you have need of for your system. So let's assume I had, for my pipeline or whatever, I just want to consider, 5 stages. Make it really pretty. A, B, C, E, A. Okay. So we're going to divide this into pieces. If this was the first run, second run, third run, fourth run, fifth run as it's going through, I wouldn't be full until this part. So this is kind of set up. Because there's still this kind of wedge of what goes up here that's going in. At this point, you're doing cleanup. When you've hit this point, once the first 4 have gone through, so I'm on the 5th one, and until the last 4, right? So if I had like 100 of these unrolls I was doing, the first 4 would be set up, the last 4 would be cleanup. So the middle 92 are going to be at this state. This is kind of like my regular run. And I'd have 92 at this state, that's what it would look like. Does that make sense? So this is what we call the software pipeline. We take E from the first run, D from the second, C from the third, B from the fourth, and A from the fifth. And as long as you keep them in that order, I schedule E first, then D, then C, then B, then A, I have no problems. So for instance, consider a single pipeline. I could have my first command be E from the first stage. And then I could have D from the second, C from the third, B from the fourth, and A from the fifth one. Now, does that mean I have to rename all these? Well, consider what would be going on. When I'm doing E from this one, from the very first stage, let's assume that E decides not to branch. If E decides not to branch, then these commands won't happen because it'll jump out. This would be one of those, jump and leave type of situations that's going on. So I could put a jump and leave on there, but that means that as far as we're concerned on these, as long as I put the memory commits for my stages, the other ones in between there, I don't let them commit before then, I'm going to be safe. So I might have to slightly rearrange my things so that in this case there's no store. All right? So I could say, well, at that point, the only thing that would have happened is, B is when I added into my running sum. Right? So I need to remove, you know, B from this stage and B from that stage. That's the only two. Right, so I'd have subtracting the B from 2 and the B from 3. So I could just come in here during the cleanup and say, you know, subtract the B3, subtract the B2, or vice versa, whatever I wanted. I could remove those effects. That's going on. Then I'd remove them from the sum. Your sum is now correct. All you care about was the sum. So from those perspectives, I've just removed the problem that was going on because I identified the couple commands that shouldn't have happened on exit, and I cleaned them up because I got this extra wedge of commands anyway that's in cleanup, so I might as well take advantage of them. Does that make sense? But during the regular runtime, would it be a problem? Well, if we're taking the thing of, hey, look, you know, E during the middle zone and it's not right, it's going to come right up to the top, no problem that E's there. The only potential that could happen is if the value of T2 got messed up by the next command. Right? So I've got this T2. I don't want this one down here. Right? So I'm calling this one E1, and this one is now technically E2 for me. I don't want this one's T2 to mess up my T2. Because I'm now slicing from different, or sorry, that's not E, that's D. Right? Or my naming problems. Right? So on and so forth. So I don't want D2 to mess up E1's value of T2. Can it? E1 finishes before D2. Or at the very least, E1 is going to start before D2 is going to start. So since E1 starts before, it'll fetch its values before this one even starts fetching its values. So therefore, can D2 finish before E1 fetches its value of T2? No, because E1 fetches before D2 gets its stuff. It's going to always do it, so this one will get its values before this one gets its values, and this one changes values after it gets its values. So there's no way this one can change values before that one can finish. So this is completely safe. There is no way for this D2 to mess up that E1. Totally safe. How about C3 messing up D2? All right, so it's the same argument I could ask whether or not, you know, C2 could mess up D1. We agree? I mean, it's not which iteration of the loop that matters, it's one to the next as it goes in. Could this C mess up that D? Well, there is a dependence between these that's going on, right?
Yes, sir.
This one's writing S0, that one's reading S0. D happens first. So that means this one reads S0 before this one reads S0. And then this one modifies S0, but after it read it, which is after it read its, so is there any way it could possibly mess up the values? It cannot mess up the value. So this one is safe. And there's no direct dependence between these two, so I don't have to worry about anything. So now we know these are all safe. How about B4? Right? There's no dependence, so right? It doesn't matter that B4 comes after. I can really tell that people are, so like half the people are snickering and the other half are like, oh gosh, it's 8 and no coffee. Right? I mean, that took a little bit of work to kind of tune up to get B4 in there. Okay. So that one, there's no dependence between this and the other, so it's safe. Does it matter that this is before A5? Yes, I'm going to milk this joke.
Was this whole example just for that joke?
No, but it worked out nicely, right? It's more that I saw this and I'm like, oh, if I number them like I always do, it won't work out well. But if I bother to switch and do a letter number thing, it'll look reasonable, but lead to stupid jokes. It's like added bonus all the way around. Okay. I might have to actually remember that for future years, right? Because if people laugh at it at 9 o'clock in the morning, it's a good joke.
The video.
What's that?
Video, you're all set.
Yeah, I know, I can, yeah, I just, walk in, play the video, and I can fall asleep in the back. Okay. Is it okay that, this is before A5? There is a dependence, right? But the dependence is, it's raw, it's read after write. So I can't have this one read after that one writes. But this one reads before this one reads, and this one reads before this one writes. Same argument. Notice that one simple argument works. By slicing them across the timeline, I've actually made it totally safe. It's kind of cool. I mean, you have to worry about the exit, and if you sum the value, you shouldn't at the end. So you have to worry about that kind of end conditions and the start conditions. But if the loop's going to happen a bunch of times, and I obviously wouldn't do this if it was going to run 10 times or something. For a 5-stage pipeline, I'd get 2 things in the middle, and I'd have 8 stuff in setup and cleanup. There'd be no benefits. But if you're doing this hundreds of times, thousands of times, right? You're talking, 99% that there's no problem. And think of the added bonus. Here's where the load is being accessed, right? This is when load happens. But then, when does it get around to the point where it's using it? Well, there's a whole 4 instructions between there. That's plenty of time for cache to fetch things. So as long as you're doing cache stuff, it's completely hidden. You will not notice any cache penalty whatsoever. That's a lot of time to actually resolve stuff out when you're going in. So I've got a lot of safety in this, actually. It hides an awful lot of problems. So it's been described as there's kind of like this little wedge of setup, and then there's this zone of pure efficiency, and then an exit. So if you're doing it for a long time, that's what you get. When you're doing the software pipelining that's going, or as opposed to software pipeline, if you're doing loop unrolling, what you get is each one, I've got its own, everything has its own little setup, and then I'm just overlapping the setups of 2 stages, for instance, to try to fill this in. Right? And then I hope between each stage, when I copy that I can fill them in. What's going on? And sometimes you can do that really efficiently and it works great. But this one, once you get it, aside from a little mess on the ends, and if I told you I was 99.2% efficient, that would be for 1,000 iterations in a loop that's going on. I'd be 992 over 1,000 would be my efficiency. You worried about the 0.8? And even that 0.8 is still going to be partially used. And maybe I can pack that, but maybe I don't care either, right? I could be good enough that I'm just like, hey, look, it's less than 1%, right? If you get a 99% speed up pretty consistently, I don't think you're worrying about it. People are fighting for much less. So it gives you some really cool techniques that you can do. The whole trick to all of these was, if you notice the way we kind of have always scheduled things, I tried to take those same things, and instead of cutting them this way, which is what we usually do, take this one and just mix them together, we cut the other direction. right? This is that kind of looking at it orthogonally thing, because it's literally orthogonal here that goes on. And it just turns out that weird side perspective is really important. And this is where I would say the real advantage comes in from people who think differently in engineering. You want a diversity of perspectives that goes on, styles of thinking. That's the most important for a good design, is lots of perspectives that goes on. How you find those are spread across people. You gotta find where it goes. But a good team, you wanna make sure you're getting people who look at the world a little bit different. If everybody thinks like you, you're gonna be stuck in a particular way of doing things and you'll never branch out of it. In order to see the best research topics happen, by being willing to take a risk and look at something crazy. And have people go, my goodness, that just, no, that's crazy, you know? And a new idea will always be crazy. And sometimes they'll be legitimate crazy and worthless. And sometimes they will be revolutionary. You gotta be willing to be crazy to do something great. And I can't tell you how many people have told me my ideas are crazy. And sometimes they were dead right, and sometimes they were dead wrong. But I'll take the dead wrongs for the few times I was right. Right? Because that's when an advancement went, and that can be kept by everybody for all time. You know. So in that sense, I also encourage you from these same perspectives, be willing to try something new, and be willing to have a very tough skin. But that's where the advantage is going to come. And you're all grad students, so boom, here you go. This is, we now chart the crazy course, right? But there's a potential for advancement there. We good? Okay, so next time I will have to talk a little bit about the GCD test. We've got the techniques here. There's one other way that something odd could happen, particularly for loop unrolling, which has to do with what if you're going through that accessing a vector and some of the vector accesses and writes are not similar. So we'll talk about that starting next time and then move on. All right, have a good day.